Okay, everybody, we're going to move to example 1. It says that we are going to repeat the track collisions on the previous section, but we are going to add ideal springs to the ideal spring bumpers to the glider so that the collision is completely elastic. What are the final velocities of the glider? So anytime that I see the word elastic, we're going to think of 3 equations, and those 3 equations I'm going to write right underneath of here when we see the word elastic. So the first equation that I think of is that initial momentum has to equal final momentum. That's an absolute. Okay? Next thing, that's always the case, right? But elastic brings into kinetic energy initial equal kinetic energy final. And it also brings you that fancy equation that we had yesterday, that if you add the initial and the final velocities of the first object, that will equal the initial and the final velocities of the second object. And we can further digest this one as m1v1I plus m2v2I equals m1v1f plus m2v2f. That's our momentum equation. And on this one we can say 1/2 mv1I squared plus 1/2 mv2I squared, so initial kinetic energies, equals 1/2 m1v1f squared plus 1/2 m2v2f squared. So that's the conservation of kinetic energy in elastic equations. So the first thing, when I come to these kind of equations, what I'm going to do is step 1, I'm going to look into my momentum equation. So I'm going to fill in the PI equals PF. And I'm going to fill it in right here. So this is the first one my mind sees is going to. We're not going to be able to solve right away. So M1 is 0.5. And maybe we should identify that. Like here's M1 and here's M2. Okay? So, and you know what? It might be beneficial for us just to label everything. I'll show you how I label it on my paper. Okay, so actually let's erase this and let's do a whole bunch of labeling to keep things organized. Let's write M1 equals 0.5. Let's write V1I equals, there it is, 2. Let's write V1F equals question mark. And let's write M2 equals 0.3. Let's write V2I equals -2. And let's do V2F equals question mark, because we don't know the final velocities. That's what they kind of want us to figure out. All right, now let's move to my first equation. I really like this one, so we're going to start over here. And you might want to keep your writing small, because when I did this, I took up a whole piece of paper to solve it, just to keep it nice and small. It would be very beneficial. So step 1, let's use our momentum. Let's use our momentum equation. Okay, I am going to write very small, so make sure you're listening to my voice. Okay, so filling in, I'm going to have M1, which is 0.5, times the first velocity of M1, so times 2, plus M2, which is 0.3, times the initial velocity of M2, which is -2. That's going to equal M1, which is 0.5, times the final velocity of 1, which I don't know, plus M2, which is 0.3, times the final velocity, which I don't know. You can solve for either V1F or V2F at this point in time. I am going to choose to get V2F by itself. So put this on your calculator, and you will get a total of 0.4. Take this to the other side, minus 0.5 V1F equals 0.3 V2F. And you're going to notice, you guys are following along pretty well, you're going to notice that matches one of Mr. McBurney's equations. To finish solving for V2F, we have to divide both sides by 0.3. So I'm going to have 0.4 minus 0.5 V1F divided by 0.3 equals V2F. That's step 1. Okay guys, let's see, I'm trying to figure out where we are. So this is kind of like step 1, equation 1. So save this, maybe put a star by it. Now what we're going to do is the second equation that I really like to use is this, this one right here, this V1I plus V1F equals V2I and V2F. So I'm going to fill that in. So V1I is 2 plus V1F is unknown. And that's going to equal V2I is -2 plus V2F is also unknown. I am keeping my handwriting small because it's a lot to take. I'm going to put this 2 on the other side, this -2, because I want to get V2F by itself in both of these equations. So if you add 2, you get 4 plus V1F equals V2F. And now the third thing that we're going to do is we're going to set this box equal to this box and cross multiply and solve for V1F. So this would be step 3. Sorry about the small handwriting. So it's going to be 4 plus V1F with some simple substitution equals 0.4 minus 0.5 V1F over 0.3. We're going to multiply both sides by 0.3 like this to use some of our Algebra 1 skills. Cancel, cancel. Multiply by 0.3. So 4 times 0.3 when you distribute is 1.2 plus 0.3 V1F. And that is going to equal 0.4 minus 0.5 V1F. Got rid of those icky fractions. Now we're going to combine our like terms. Take the 1.2. How am I doing? I think good. It doesn't really matter. Let's take this guy. Let's take the V1Fs to the other side, so we get a 0.8 V1F. Subtract 1.2 from 0.4 to get a -0.8. Divide V1F is -1. If you guys hear my child's whining about doing her math, it makes her mom feel very encouraged. Okay, now we got V1F done. So you can take, this is great. That kind of means that this guy, may as well fill this in, he's going -1 meters per second after he bounces of the other guy. Now, hopefully we get a positive number for this one since it's traveling right. Put it in here or here. It does not matter. I'm going to choose to put it in the easier one. So this is step 4. 4 plus V1F equals V2F. Just enough room to squeeze this in. 4 plus -1 equals 3 meters per second for V2F. All right, and I think we have everything. The only thing that I did on the side that I thought would be really cool is if I checked if I was right by finding the kinetic energies. So I'm going to turn this sideways and I'm going to show you that we're right by doing KE initial equaling KE final. Because this is an elastic collision, kinetic energy is maintained. So 1/2 of my first mass, 0.5, times my initial velocity of 2 squared, 1/2 mv squared, plus 1/2 of my second mass, 0.3, times my initial velocity of my second mass, -2 squared. Sorry, no, that's really small. I'm going to prove that that equals 1/2 of my first mass times the final velocity of my first mass, -1 squared, plus 1/2 of my second mass, 0.3, times my final velocity of my second mass of 3 squared. I love that that was positive. We're going to prove that the left equals the right. This is elastic, so we have to do our math right. This will work out. Let's try. 0.5 times 0.5 times 2 squared plus 0.5 times 0.3 times 2 squared. I just negated the negative. So I get a 1.6 for my initial kinetic energy. And let's try the right side. I'm lazy, so I'm not going to put my negative in there. If I was going to put my negative in there, please remember you need to use just parentheses like that. Okay. Plus 0.5 times 3 times 3 squared. 1.6. So there you go, guys. We just proved that everything we did was really, really good. All right, let's move on to example 2. I have a little nervous about doing number 2, only because I haven't done it on my own. But I'm kind of at that point where I'm just about to meet with you, so I need to hustle up. Oh, look, Mr. McBurney doesn't have an answer key on example 2. I'm going to pause the video and look it up online just to make sure I get the right answers. All right, example 2, I couldn't find any answers anywhere, but I feel pretty confident. If anybody notices that I make a silly mistake, please let me know, okay? The fission of a uranium nuclei in a nuclear reactor produces high-speed neutrons. Before such neutrons can efficiently cause additional fissions, they must be slowed down by collisions with the nuclei in the moderator of the reactor. The first nuclear used carbon as a moderator. Suppose a neutron with a mass of 1 U, excuse me for not knowing what that means, travels 2.6 times 10 to the 7th meters per second, undergoes a head-on collision, initially at rest, neglecting, okay. Now, I don't believe we need to change this to kilograms. I think we can just know that everything is in the same units. So let's go ahead and approach it that way. I'll send a picture maybe to Mr. McBurney and he can make sure that I'm good in what I'm saying. All right, yeah, because like masses cancel out in that one equation. All right, let's go. So we have M1. Can you see? Yeah, you can read. M1 is, I guess they have an N. We can, okay, for, is it nuclei, I guess? Yeah, uranium nuclei. A neutron. This is a neutron with a mass. Okay, so 1, the initial velocity of that object, I guess they can use an N here since they, instead of using a 1, they used an N. Doesn't really matter. Let's see. 2.6 times 10 to the 7th. It's really fast. We do not know the final. That's what we need to solve. And now we have this other mass, C. I think we're in carbon. Carbon nucleus, and that is 12. And the velocity initially is 0, and the velocity at the end is unknown. So let's start with our the fact that a momentum, we conserve momentum. So I'm going to do mass, I'm going to do the mass times the initial velocity plus the other mass times its initial velocity equals the first mass times its final velocity plus the second mass times its final velocity. And then those two are unknowns. I'm going to get this one, no, I'm going to get this one by itself because I like to divide by 1. So get my calculator to get that side worked out. Silly me, there we go, let's try again. 2.6 times 10 to the 7th plus 0, okay? And then we're going to subtract this to the other side. So we have 2, 6, that was silly of me, I didn't need to do that. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 6 makes 6 zeros. And minus this 12 VCF equals 1, so negate the 1. You can divide by 1 if you want to. VNF. Number 2. Remember that really cool thing you can use for elastic collisions? Remember that really cool thing I did yesterday? The VNI plus VNF equals VCI plus VCF. What I love about this is that it turns into 0. This one turns into 2.6 times 10 to the 7 plus VNF equals 0 plus VCF. I'm going to get VN, since I got VNF by itself up here, I'm going to get VNF by itself down here. So VNF equals VCF minus 2.6 times 10 to the 7th. You can make that 26 million if you want to. And now step 3, use some basic substitution. Set this box equal to this box so we can solve for So 26 million. If you're wondering why, like on one of them I looked in scientific notation, the other one I didn't, the answer is, I don't know, equals, it doesn't matter, VCF 26 times 10 to the 7th. Good, you can still see, move up a little bit. Add that to the other side. Look at that, we don't even have any like distributing coefficients. I don't think I screwed anything up. Please let me know if you guys see anything dumb that I did, but I think I'm okay. So right away, VCF is going to be way easier than, wait, yeah, I'm good, right? Check up there. I think everything looks really nice because, yeah, that one was a 1. I didn't have to do any of that crazy weird division stuff. Okay, just making sure. So add this to the other side. So you're literally just doubling it, aren't you? So 5, 2, 1, 2, 3, 1, 2, 3 meters per second. When a number's that big, we should probably put it in scientific notation. Kind of makes sense to me. So that's fast, right? It's at rest. Trying to think if I'm happy with that answer or not. Seems like it's too high. No. Well, let's go ahead and check out step 4 and see what we get for step 4, and then we'll check our kinetic energy, okay? So step, hopefully it's right because I really don't want to redo this video. So we're going to take this answer and plug it in right there. Okay, or right here. It really doesn't matter. Just looking. Something did not go right. I'm going to pause the video. Hey guys, hopefully you're able to figure out the silly mistake I made. Things are not adding up. It was right here. When I did this box equals this box, I completely forgot about the minus 12 VCF. So pause the video and erase if, or maybe you guys were able to catch my mistake before. Okay, now I'm going to carry this over here. So we have 13 VCF. That looks a lot better. Add this over here. So we do actually have this 52 million. I just didn't divide it by 13. Hey guys, I made another mistake, but I'm going to try my best to trim it out and come back to here. So I'm happy with this answer here, but when I divide by 13, I get 4, and it's followed by 6 zeros. Okay, everybody. So this should have been 10 to the 7th. I will learn how to count in some point in time in my life. Today's just not the day. So when I come up here, I'm going to write negative 2.2 times 10 to the 7th. And over here, I'm going to write 4 times 10 to the 6th. So now when I check it, I'm going to get it right. I promise, because I've tried it like 4 times. Okay? Here we go. 1/2 times my mass times my first velocity squared. That's the number I get. And that needs to equal 1/2 times my first mass times this velocity squared. So since it's negative, when you square it, it goes away. So here's what I'm going to do. I'm just going to do 22 with 6 zeros. Okay. Plus 1/2 my second velocity, mass of 12, final velocity 4 with 6 zeros squared. I'm good. Kinetic energy is conserved. That was very exciting. I'm going to post this video to YouTube and hope that I can make it through the next lesson.